let's just review what we learned last time. Last time we talked about the thermochemistry, talk about heat. Okay. We talk about some of the concept. First of all, the system and the surrounding. Okay, system is the one that we're looking for. We're watching the space or the universe we were watching, and surrounding is the rest of this, not including the system. Okay, yeah. So system and surrounding is coupled. But if we talk about the heat change, we always talk about the system, the heat change for the system. Okay. And we talk about heat. Heat is energy that is used to changing the temperature. So some of this, the energy has a different energy: heat, kinetic energy, potential energy. But heat is used to change the temperature. So the temperature change, and we're going to have the heat change. Okay, the flow of the heat is always from higher temperature to a lower temperature. Okay, that's a flow of heat. Always from higher temperature to a lower temperature. So it really doesn't matter what kind of size of this object. Okay, as long as the object has a higher temperature, they're going to moving the heat from the high temperature to the lower temperature. And the heat transfer has a direction. So we are going to have two different kind of the process or direction. One is called exothermic. The other one is called endothermic. So exothermic, that means the heat transfer out from the system to the surrounding. So this is exothermic. Okay. Some of the reaction, like you're burning wood, or you're burning things, and those are all exothermic because we giving out the energy, the system is releasing energy, releasing the heat. So the system will lose the heat, it transfer out. Endothermic is gaining the heat. We're gaining the heat, so the system gain the heat. Okay, or system absorbing the heat. So the heat is transferred to the object. And we talk about the heat has a sign. Okay, exothermic, the heat is a negative sign. Endothermic, the heat is a positive sign. So the heat is all talk about the system. So system losing the heat, then is exo. System gain the heat, that's endo. Okay, and we also talk about the some of the process. Okay, phase change can also be endothermic or exothermic. Okay, you can think about the temperature for the phase. The solid, liquid, and the gas will have a different temperature. Okay, if you're from low temperature phase to the higher temperature phase, definitely the system or this object needs to absorb the heat to make this temperature go higher. Okay, so that's an endothermic. But if you're from higher temperature state like a gas to drop down to the lower temperature phase like solid, which is deposition process, and then this is exothermic because you need to cool down the object to let it become a solid. Okay, so if you're just think about the temperature, then you generally know, okay, what phase the phase transfer gonna be what kind of process, endothermic or exothermic. Again, endothermic is gaining the heat from to the system, and exothermic is producing heat from the system. All right, okay. And last time we also talked about the unit of heat. Most of the case we're using joule and kilojoule for the experiment. Kilojoule is the most of case. Kilojoule is 1,000 of the joule. Okay, 1,000 of joule. So later when we do the calculation, you need to be careful about the unit. Okay, yeah. We also talk about calorie and food calorie. The kcal, food calorie, is the most common unit that we're using when you eat some of the food product. the unit temperature, unit of temperature, unit conversion. Most of cases, we're just looking at this, the Kelvin to Celsius, Celsius to Kelvin. Kelvin always bigger than Celsius, the unit, the number always bigger. So Celsius plus 273, then you got Kelvin. Kelvin subtract 273 will be Celsius. Okay, will be the Celsius. And Kelvin do have an absolute zero over here. That zero is absolute zero. At this moment, at this temperature, nothing can move, including the atoms and molecule. Last object, we talk about specific heat. Okay, specific heat capacity or specific heat or SP heat. They talk about how much heat we need for 1 gram of object raise the temperature by 1 Celsius. Okay, so the bigger number of the smaller number of the specific heat means they are going to raise the temperature much faster. Okay, the bigger number of the specific heat means they're going to increase the heat, the temperature much lower. Okay, because they need to absorb quite more energy to raise the temperature. Okay, so that's why the water can be used to transfer the heat as the agent for the air conditioner. Okay, with the cool down things. And also that's why the swimming pool is still cool in the summer. Okay, even the rain of the swimming pool is really hot, but the inside of the water, that's going to be much cooler. Okay, yeah, they're absorbing the same energy, but water going to be much cooler because they have a really high specific heat. They need to absorb quite more energy to raise 1 Celsius. Okay, rather than some of the concrete. It just the specific heat of concrete is pretty low. They just need a heat absorb a little bit heat, and the temperature of those will increase. Okay, yeah. All right, so this is what we talked about last time. Last part we talk about one equation, which is this: heat equal to specific heat time mass time final temperature subtract the initial temperature. And this is talk about, well, we know when the temperature of the object increase, they are going to absorbing the heat. Now, how much heat they can absorb? And this is the equation that helping us to figure out how much heat that one of the object, if we raise the temperature, how much heat this object will receive. Okay, so heat equal to C time M time final temperature subtract the initial temperature. C, capital C, is the specific heat. Okay, capital C is a specific heat. Okay, so now we can just using this equation to do some of the practice. Okay, so this is the study guide. Already have the study guide here. So tap on the study guide. Okay, so now here, the first one, let's look at it. It talk about a sample of 54 grams of the methanol is heated from 25 Celsius to 35 Celsius. How much heat is required? You see, we change the temperature of this object, then this guy definitely need to absorb the heat to raise the temperature. How much heat we can increase they need. So Q, which is the heat, equal to specific heat, capital C, time M, which is the mass, and time final temperature, subtract initial temperature. Okay, so those are all when you have a time multiplication in between. So heat, you need to find the specific heat. What is specific heat? This is a specific heat. And if you look at the unit, okay, very important. I'm going to talk about, we're always looking at the unit. Specific heat the unit is joule per gram per Kelvin. So that is a species heat. Some people also would like to write a joule, gram to the negative order and a K to the -1 order. Okay, it's the same thing because the -1 is just 1/G. Okay, yeah. So this unit is the same unit. Those two are equal to each other. So this is a unit for species heat, gram, joule per gram per K. Okay, and also the species heat sometimes can also write like a joule per gram per Celsius. Okay, so this is K, this is Celsius. This is talking about the species heat. But just telling you the species heat, those two units, 1 joule per gram per K is equal to 1 joule per gram per Celsius. Unit is the same. The Kelvin and the species heat, the Celsius here is talk about change of the temperature. See, this is change of the temperature. So that's why change of the temperature in Kelvin and a change of temperature in Celsius is generally is the same thing. Okay, yeah. Your increase 10 Celsius in Celsius is equal to your increase 10 Kelvin in Kelvin. Okay, so now you can see species heat we got is a 2.48, and this is joule per gram per Kelvin, and you multiply the mass. The mass have to be in Kelvin. The mass must be in gram. If the mass using kilogram, then you need to change that unit because the unit for species heat is gram. So this is time 54.0 gram. Then you're going to multiply final temperature, subtract initial. Which one is the final? In this case, which one is the final temperature? 35. Okay, 35 Celsius is final. You subtract 25.0 Celsius. Okay, so if you look at it here, this is a 2.48 joule per gram per K times 54.0 gram. And your time, this is a 10.0 Celsius. And we talk about the change of the Celsius is equal to the change of the Kelvin. So 10 Celsius, this change is just equal to 10.0 Kelvin. Okay, those are the change is the same. Not the absolute number is different, but the change is the same. Okay, yeah, the change is the same. So if you look at the units, gram and gram canceled, Kelvin canceled. So left over is just in joule. So that's why when you calculate, you figure out the joule. Put in the calculator 2.48 times 2.48 times 84.0 times 10. And you got 1339.2. 1339.2. And this unit is in joule. This is how much heat that absorbed. And if you look at the sig fig, well, this one 3 sig fig, 3 sig fig, 3 sig fig, 3 sig. So everything is 3. So you're going to keep a 3 sig fig. So the answer will be just 1, 2, 3. And look at the next one. Next one is 9. So you run up, which is 1340. And this is in joule. Here it is. Okay, so pretty straightforward, right? If you know the equation, then you should be able to solve the problem. Okay, yeah. So this is just the one of the cases. But I would like to do more deeper. Okay, would like to talk about more deeper the case, how to do some of the extended problem. Okay. Yeah. take a while. By the way, today we do have a lab, but I didn't see what kind of lab we are going to do and what kind of template. So today we're going to do lab 40, but this lab, you don't need to do anything. You just need to prepare the solution for the lab 50, okay? So lab 40 is the preparation lab. You don't have to write the report, okay? Yeah, you don't have to write the report. It's just a preparation to making some of the solutions, okay? Making some of solution. Okay, so I would like to talk about a little bit deeper on this kind of heat capacity part. So let's talk about one of the situation. If we have a container, and this container is a sealed container, okay, which means there's no heat transfer from outside to the inside because it's sealed, it's isolated. So the heat cannot go out, just like a thermal cup, right? If you cap the thermal cup, it will keep the heat for at least like 12 hours. Well, so we assume at that condition, there's no heat exchange from inside to the outside, okay? So, but they do have a heat exchange inside of this container, okay? So the situation is, what if we have a water in this situation, and this water has only just 10 Celsius, 10.0 Celsius, okay? And we're going to have a small metal, and this metal is pretty hot, probably is 105.0 Celsius. So we have a very, very hot object, and then this hot object is going to drop into the hot water, the cold water. Then can you imagine what happened? In the hot water, dropping the the hot object dropping the cold water. What is the temperature change for those two objects, water and metal? Yeah, so the metal temperature goes down and the water temperature goes up, right? That makes sense, right? And so this is what we talk about heat exchange, right? Heat do exchange, which means the metal transfer their heat to the cold water, right? Because we talk about the heat transfer from higher temperature to the lower temperature. So the water has a lower temperature, definitely the metal gonna transfer the heat to the water, right? So heat exchange, because we know energy cannot be destroyed or generated, which means how much the metal transferred heat must completely be absorbed by the water. That makes sense, right? Okay, so now we can set up an equation, which is the heat that the metal transferred should be equal to the negative sign of the heat, the water gain. Okay, so this is heat. How much heat metal transferred heat should be equal to how much the water gain. The absolute value should be the same, which means the Q value should be the same, but they do have a negative sign over here. Think about it. One is gaining the heat, one is absorbing heat. So they have the sign difference. That makes sense, right? They have a sign difference. So this is the first setup we can do. The heat, how much metal got transfer should be equal to how much water gain. And then we also know Q should be equal to species heat times metal, time mass divided by final T minus initial T, right? Yeah. So what happens in this situation, if we draw a graph, you will see, and if we talk about this is temperature, at the temperature for the metal, this is metal in the top, and this is the water in the bottom. So metal has a higher temperature, 105.0 Celsius. Water has just a 10.0 Celsius. So, you know, the water will increase the temperature, but the metal will decrease the temperature. when eventually they're going to stop, right? The heat transfer will stop, which means they're going to reach to a certain time point. And at this certain time point, doesn't matter it's a metal or water, the temperature will be equal. That makes sense, right? So the temperature will be equal. So the water will go down to the certain temperature, will go up to a certain temperature. Metal go down to a certain temperature. At this temperature, all of those objects has the same temperature. And then there's going to be no temperature, heat transfer. Okay, heat transfer stop when the temperature is the same, right? We talk about heat transfer have to from higher temperature to lower. If they do not have a temperature difference, then the transfer will stop. Okay, yeah. So those are the same thing. So based on this equation, what we can do, we can using this equation to apply in both two objects, water and metal, right? And this equation, as long as we know the specific heat of metal and the mass of metal and change of the temperature for the metal, and we can write specific heat of the metal, you multiply the mass of the metal, and then your time final temperature of the metal, and see we know the final temperature and for the metal and water is the same, so we don't have to write the other one. So just final temperature subtract the initial temperature of the metal. This is what we have for the metal parts, right? Then this is also should be equal to the specific heat, negative sign of specific heat time of the water, right? Specific heat of water, right? Because the equation can be more, doesn't matter what kind, as long as those are feet. Specific heat of water, time mass of the water, and the time final temperature of the water subtract the initial temperature of the water. That makes sense, right? So you generally you can using all those equations to represent. This equation represents heat of metal, and this equation represents heat of water. Make sense, right? So now let's see how many unknown we have. How many parameters in this equation? We have 1, 2, 3, 4, 5, 6, and 7. We only have 7 unknown. I mean, final temperature is the same thing. Okay, so only 7 unknown. In another word, if we know 6 of those unknown, and the last one should be able to solve. That makes sense, right? I mean, this is just a normal math question. Okay, so that is why we can use this equation to solve some of the other questions. Let's just look at it. The second equation, second problem. Okay, so this problem is that we have a piece of copper. So here we have a piece of copper, and this copper metal, it has the temperature is 176.0 Celsius. And this one is placed in an isolated cup containing 10 grams of the water at 20 Celsius. Okay, so the final temperature of this mixture is 21.18 Celsius, which means when they mix the metal and water, the water raises up the temperature, but just raise a little bit. But it didn't say how about a metal, but obviously metal will be the same temperature, just like the water temperature. And what is the specific heat of the copper? So they are looking for the specific heat of copper. They give you the specific heat of water. Okay, and once again, then let's just see this equation. Okay, let's just looking at this of the equation. Let's see what we have. We have, for this kind of equation, it's better to list what we have. The mass of metal, we know, 0.825 gram. And the specific heat of water, we also have 4.184 joule per gram per Kelvin. And the mass of water, we also have, which is 10.0 gram. And initial temperature of the metal. What is the initial temperature of metal? 176.0. 176.0 Celsius. And the initial temperature of water is 20.00 Celsius. Okay, so now we already, based on the list, we already know 1, 2, 3, 4, 5, right? We talk about here, we have a 7. I think we should have one more, the final temperature. The final temperature we also know, which is 21.18 Celsius. So now we know 6, right? We talk about there are 7 of unknown over here, but we know 6 of those unknown. So we should be able to solve the last one. And then we can just go ahead. Once you set up this equation, then you can go ahead to plug those parameters into these equations. So we have they are looking for what? They are looking for the species heat of metal, okay, which is copper. So the species heat of the metal should equal time the mass of metal, which is 0.825 gram, and equal time the final temperature subtract the initial. Final temperature is here 21.18 Celsius. Subtract the initial. The initial is 176.0 Celsius. So that is the what we have on the left side. And then let's finish what we have on the right side. That should be equal to the negative sign. Make sure that the negative sign is very important. Sometimes sometimes I happen to forget this. If you miss the negative sign, then your calculation is completely wrong. Okay, yeah, negative species of water 4.184. This is joule per gram per Celsius, and then multiply the mass of water, which is 10.0 gram, and the final temperature, which is 21.18 Celsius. Subtract the initial temperature of water, which is 20.00 Celsius. You see, everything on the right side is number, so you can figure out. Everything on the left side, only just the species heat of metal is unknown. So we should be able to solve problem. Let's just rearrange this equation. So on the left side, what we can have is 0.825 times 21.18 subtract 20, subtract 176.0. So we got negative 127.7265. So species heat of the metal time negative 127.7265. And on the right side is 4.184 negative, your time 10, your time 21.18 subtract the 20. You got another number, negative 52.9112. Negative 52.9112. And this is in joule. When you solve this problem, I believe this is the unit here will be gram times Celsius. Okay, so now you have this unknown. So once you have this, what do we do? You're divided by this number on both sides, right? You divide by this number on the both sides. So you're gonna have a species heat of this metal that should be equal to negative 52.9112 joule divided by negative 127.7265. And this is gram Celsius. And then you say negative is canceled. 52.91112. 52.9112 divided by 127.7265. And we got a number. And wait, let me double check. Did I do wrong somewhere? The answer shouldn't be 0.4 something, should be 0.38. Where did I got wrong? Okay, let me just calculate that one more time. Oh, okay. So this part we calculate wrong. So this one how come 4.18 4 times 10 times 21.18 subtract 20. What?
It's supposed to be 9.
Yeah, I know. But this value should be okay, so 49.3712. $49.3712. 49.3712 divided by 127.7265. Yeah, that makes sense. Okay, so 0.387. 0.387, and this is in joule per gram per Celsius. Okay, yeah. So this is one of the case. Here, this is talking about the heat exchange in an isolated system. Okay, yeah. So something giving the temperature, something giving the heat, and something absorbing the heat. Okay, so this is one of the cases. So I would like to, okay, so now we understand the concept. Let's work on the question number 7. So look at this one. This one, okay, this is not talking about the metal, but they talk about the water. We put a hot water into a cold water, and what is the case? So here is that what is the final temperature? We're looking for final temperature when 20.0 gram of water at 80 Celsius is mixed with 30 gram of the water at 20 Celsius in an isolated system container. So here there's no metal, but we're putting hot water into a cold water, and what is the final temperature? Well, but the concept is the same thing, right? So in this case, the concept is still there. What happens once you have a hot water mixed with cold water? It's the same thing. Hot water is going to produce the heat, transfer the heat to the cold water, which means how much the hot water release the heat should be gained by the cold water, right? So you still can set up the equation. So I give you like 2 minutes to set up the equation. Don't have to do the calculation, but please set up the equation. What kind of equation we need? how much the hot water gave should be equal to how much the cold water gained, right? So once you set up the equation should be just the Q of the hot water should be equal to the negative sign Q of the cold water. Well, if you write the Q of the cold water equal to negative sign of Q of the hot water, that's the same thing, okay? Those are the same thing. It doesn't matter. It really doesn't matter where the negative sign shows up here, okay? As long as those two have a negative sign, then that's it, okay? Yeah. So, so this is the equation, and then you can extend this equation, okay, by using Q equal to C time M time delta T, final temperature subtracting initial. So here on the left side is hot water, and then you just need to have specific heat of the hot water. You multiply the mass of the hot water and multiply the final temperature of the hot water, which is hot water and cold water should be the same. So the final temperature is the same. Subtract the initial temperature of the hot water. This is what we have on the left side. That should be equal to the negative sign, specific heat of the cold water, time mass of the cold water, and the time the final temperature subtract the initial temperature of the cold water, right? So let's see what we have. We have, this is the mass of the, this is mass of the hot water. This is the initial temperature of the hot water. The 30 is mass of the cold water. 20 is initial temperature of the cold water. And what else? And also we have a specific heat of water. Okay, so this is what we have. And just to let you know, the water, as long as they are the same liquid, those are all the water. So the specific heat is the same thing. Okay, specific heat is not being changed. Right, we talk about specific heat just like a density. It's an intensive property. This property will not change. Okay, as long as they are keeping the same state. Okay, so hot doesn't matter, it's hot water, cold water, those are all water. So the specific heat is not going to be changed. So once you set up this equation, what you need to do is just plug all the numbers in there and try to solve the problem. Okay, so let's see, specific heat, that's a 4.184. Is a joule per gram per cell per Kelvin. And then multiply the mass of hot water, which is 20.0 gram, and time the final temperature, subtract the initial temperature. The initial of hot water is 80.0 Celsius. All right, this one is equal to negative specific heat, still 4.184 joule per gram per Kelvin, time mass of cold water, which is 30.0 gram, and the time final temperature, subtract the initial, which is 20.0 Celsius. Okay, so this question, this equation need a little bit math. Okay, you need to solve this with math. You need to combine those unknowns all together. But first of all, let's see, we have 4.184, 4.184 on both sides. So definitely this part can be canceled. Okay, so we don't worry about that. And then you will see we have 20 T minus 80 equal to negative 30 final T subtract 20. Okay, so this is an equation that you're going to do. So first of all, you need to contribute the 20 to the each of this. Okay, this is called contribution, right? I forgot how the math. What is the term when you do this? A distribution, not contribute. Okay, distribute. You're gonna distribute this. So the 20 times TF and the 20 times 80 minus 80. So you have a 20 TF subtract 20 times 80. And this one, you're going to do the same thing, distribution. Negative 30 times TF, and then plus negative 30 times negative 20. Okay, so this is what we're gonna do. And then once after the distribution, you just need to move the unknown to the left side and move the number to the right side. That's it. So the unknown, this is on right side is negative 30 TF. You move to the left side, you change the sign. So that's going to be 20 TF plus 30 TF. And then the number you will see just make sure I did right. Yeah, I think I did right. Yeah. So in this case, there's gonna be so 20 times 80, that's 1600. Negative 1600 on the left side, and then 1600 on the right side. And then your plus 30 times 20, which is 600. Negative, negative become positive, so plus 600. Okay, so now you have a 50 TF equal to 2200. So the final temperature will be just equal to 2200 divided by 50. Then you got 44 Celsius. Okay, so the temperature, they're going to the 44 20 Celsius. So this is also makes sense because you see the hot temperature, that's 80, cold temperature is 20. So when they mix, those two mix together, the temperature should be something in between, right? The 44 is something in between. So that is why if you have the final answer, then you can double check. Is this final answer in between those two numbers? If it's out of those two numbers, then definitely they got it wrong. Okay, yeah. So you need to make sure this final answer should be in between this. Okay, in between this. That makes sense, right? Okay. And again, the reason I'm giving you the study guide is I'm hoping you to do the practice. Okay, yeah. I hope you're to do the practice. If you're not doing the practice, it's really, really hard for you to understand the parts. You have to do the practice. Okay, yeah, you have to do the practice. And then we can there's one more let's take a break. Okay, let's take a break and then we will talk more.
I'm gonna miss the next Thursday's class. Be out of town. What am I gonna miss? Like part of the lab?
Yes.
Okay. So
Okay, so let's look at another question, still talking about the heat exchange over here, the question number 6. But this one is another situation, okay? So we talk about, beginning, we talk about the hot metal into the cold water, hot water into the cold water. And they also some cases, when we dissolve things today, when we dissolve sodium hydroxide, we're making sodium hydroxide solution. I would like everyone to touch the bottle, the bottom of the bottle, okay, to see whether is there any heat. So when you dissolve the sodium hydroxide, generally it's an exothermic process, okay? They're going to produce the heat out. So you should feel warm on the bottom of the bottle, okay? Yeah, so this is also the same thing. They have a sodium hydroxide that dissolve in the water, okay? So if we have sodium hydroxide dissolved in the water, then the whole solution, sodium hydroxide solution, is going to be heated up, right? So this is what happens. Not just the water got warmed, the sodium hydroxide itself also being warmed up. That makes sense, right? Yeah. So here, this is also we talk about. Here we talk about determining the heat. We have a sodium hydroxide added into water. Calorimeter is what we call the insulated system. Okay, so if you see calorimeter, generally it's just an insulated system or isolated system. Okay, yeah. The temperature was monitored as the sodium hydroxide dissolved to give the data below. So we have a table over here. And then they are looking for determining the heat released during the solution process. So we're dissolving sodium hydroxide. They're producing heat. How much heat that they generate during this process? Okay. So now we also still can using this equation. The heat they generated, right? The heat generated. So the heat generated should be equal to the specific heat of the solution. Okay, you have to know this is a solution, right? Because the whole solution is warm up, not just the water. Sodium hydroxide itself also be warm up. So specific heat of a solution multiply the mass of the solution, and then you multiply the final temperature, subtract the initial temperature. Make sense, right? Still doing the same thing. You still have this. As long as we know everything, we should figure out how much heat they are released in this process. And then you will know what is the specific heat of the solution. Here it says, assume the solution specific heat is 4.18 joule per gram per Kelvin. So it's just 4.18 joule per gram per Kelvin. What is the mass of solution? Just to let you know, it's not 100 grams. Okay, 100 grams is just the mass of water. So what is the mass of solution? Yeah, it's 110 grams because solution is a solute plus solvent, right? This is what we talk about. So solute is 10 grams, solvent is 100 grams. So the mass of solution is just 10 plus 100. And then you multiply the temperature change. Final subtract initial. Final is 48.2 Celsius. Subtract initial 24.0 Celsius. Make sense, right? Yeah. So this equation can be in different variations. Okay, different variations. When we release the heat, we can also do the same thing like that. We release the heat by using the release the heat in the solution. They're doing the same thing. Okay, the only difference is you need to think about this is the whole solution got warm up, not just water. Okay, yeah. So now you can again plug this into your calculator. 4.18. Your time 110. Subtract a time 48.2. Subtract 24. And you got 11127. 11127. And this is in joule. But if you look at the sig fig, 5, 4, 2, 3, 3. So generally, you should be able to keep 3 sig fig in this case. Okay, so the answer, this is not right. Exactly right. You keep 3 is 1, 2, 3 over here. And look at the last one. So the answer should be just 11100 joule. Okay, yeah. This one is keep 3 sig fig because the 2 here is lower than 5. So lower than 5. So we need to round those to 0. That's it. That makes sense, right? Okay. So this again, we're talking about 3 different situations. It could be the different object. They mix them together, but still, you just need to remember how much the hot object produce the heat should be equal to how much the cold object gain. Okay. It could be just the same object like water, hot water, cold water, and it could be in some situation in the solution. Okay, but generally it talk about the similar thing, and we're using the same equation. Okay, yeah. So this is the first important parts for the thermochemistry, and the next part I'm going to talk about another object and topic. Another topic that's going to be called delta H. Delta H, which is called enthalpy. Okay, enthalpy. Okay, so H is called enthalpy actually. H is called enthalpy. But the delta H is called the change of enthalpy. Change of enthalpy. In most of the cases, in chemistry, we're care about the change of enthalpy. We're not care the enthalpy itself. Okay, the concept for the enthalpy is complicated. The enthalpy is talking about the work plus energy. Okay, so the internal is talking about internal energy plus the work is equal to enthalpy. Okay, yeah, you don't have to worry about that because I'm not going to do any of the calculation about this. Okay, but you need to understand enthalpy is just energy, the overall internal energy plus work. So that is the enthalpy. But the change of the enthalpy is much easier because the change of enthalpy is just equal to heat. Change of enthalpy is just equal to heat, but they are under a condition. When reaction is under constant temperature and pressure. So when we have some of the experiment happened under the constant temperature and pressure, you can assume the enthalpy change is just equal to the heat. Okay, the enthalpy change is just equal to the heat. But this is most of the situation is true. Current situation, current environment just have a constant temperature and a constant pressure. So that's why when we talk about most of the situation, the enthalpy change is just the heat. Okay, yeah. So you can just remember, okay, enthalpy change is just the heat. Okay, that's it. Okay, enthalpy change is just the heat. Enthalpy change is just the heat. So if the heat has a property, has a sign, the enthalpy also, the change of the enthalpy delta H also has a sign. So the delta H also has a sign. So delta H is smaller than 0, is just equal to the Q. It's just equal to Q smaller than 0. Those are the same thing, okay? Q smaller than 0 is equal to delta H smaller than 0. And this is talking about the system lose heat. System losing heat, then the temperature goes down, and this is exothermic. Okay, so delta H smaller than 0 means exothermic process. Okay, or exothermic reactions. There's exothermic. The delta H larger than 0, then that means Q larger than 0, and that means the system is gain heat, and the temperature will goes up, and this is endothermic process. Okay, this is endothermic. Okay, that's just maybe not temperature goes up, but this is definitely is exothermic or endothermic. Okay, so this is the meaning for the sign for delta H. Larger than 0, smaller than 0. Smaller than 0, that means the system losing the heat. So that's exo, will produce or generate, release, okay, the heat. Larger than 0, that's gaining. So we have an endothermic. Okay, so this is delta H. And for each of the chemical reactions, doesn't matter what kind of reactions, as long as we have a chemical reactions, they always has a delta H with it. They always has a delta H with it. Okay, in the unit 1, unit 2, we're not talking about the heat. Okay, thermal chemistry. So when we write the equation, we're not having the delta H with it. But in this unit, we're dealing with the heat. So that's why when we write the equation, we're going to write a heat with it. Okay, so for example, if we have A plus B, and then they're going to form 2C, and then they're going to have a delta H with these equations. Okay, with this equation. So the delta heat will be something, right? If the delta heat, for example, is equal to negative 100 kilojoule. And what does that mean? Negative 100 kilojoule. First of all, you look at the sign. The sign is negative sign. So what kind of reaction it is? It's an exothermic reactions. So you can base on the sign to figure out this is an exothermic reaction. Okay. So if you have A plus B, then to delta H, if this is a positive 100 kilojoule, then this means is endothermic. Okay, so the sign is telling you this meaning. Okay, the sign telling you this meaning. Let me move this. Sometimes you may also see the people write like this: A plus B equal to 2C and plus heat. Okay, so that means after this equation, you can think about the heat. If it's an exothermic reaction, they're producing heat, right? And you can think about the heat is part of the reactant, or the part of the product, right? It's producing heat. So A plus B equal to 2C plus heat is just equal to delta H equal to negative sign, because they're exothermic, they're producing heat. Okay, so those are the same thing. Okay, those are the same thing. But this one is the most common one that people write. Okay, They give you a chemical equation and they write down what is the sign of the heat. Okay. So if the exothermic like this, how about endothermic? And you can think about endothermic is the heat can be like a part of the reactant, okay? Because they absorbing the heat. We need heat to make the product, right? Yeah. So in this case, the heat, and you're going to plus A and plus B to form 2C. And this is the same thing, and it represent endothermic because this heat, which means we need 100 kilojoule of the heat plus this to make 2C. Make sense, right? Yeah. So, but again, still the top part is the most common expression that people write. Okay, yeah. So now you will see the expression, actually the heat and this equation is combined together, right? The heat and the equation is combined together. Let's just talk about a real case. For example, we have some of the equation. We have methane gas is going to react with 2 oxygen gas, and then they're going to form CO2 gas plus 2 water, and this is a liquid, and the delta H in this case will be negative 890.4 kilojoule per mole. Okay, yeah. So this, we have equation and we have a delta G, a delta H, and you see this is negative sign. So definitely this reaction is an exothermic reaction, which is makes sense. This is combustion reactions. Okay. And one thing when we talk about thermochemistry, the state is very, very important because different state means different temperature, right? This is a liquid water. And if you change that to the gas water, that means the temperature is different. So the heat will be different, right? So state for each of the species, reactant or product, very, very sensitive in the thermochemistry. And if you write a different, the state, the number of here will be changed. Okay, the number will be here will be changed. So we have this equation and this enthalpy is like this. So what the meaning of that? The meaning of this and what's the meaning for the enthalpy here? That means if we use up 1 mole of the methane, and then they are going to react with 2 mole of the oxygen, 1 mole of the methane gas, react with 2 moles of the oxygen gas, then they're going to produce 1 mole of the CO2 gas, and then they're going to form 2 moles of the water liquid, and meanwhile they're going to produce the heat, negative 89.4 kilojoule of the heat. Okay, so this is the meaning of that, and this is why this shows this is per mole. The per mole is talk about per 1 mole of this whole equation, per 1 mole of this whole equation. So we're using that much producing the heat. So the mole, how much moles is exactly just the same, just like the coefficient. Okay, yeah, are you clear? So that is why here the stoichiometry is built up, is linked. You can be using the moles of this, each of the equation, each of the species, and then you can figure out how many heat they produce. For example, 1 mole of the methane after this equation, we can produce that much of heat. How about 2 moles of methane? That's a stoichiometry, right? Then the ratio is just 1 moles of this producing that much. 2 moles of the methane, it just double that. That makes sense, right? Yeah. And I'm not sure whether you realize the reason you know 2 moles of the methane is double this is generally your setup the ratio over here. This divided by this should be equal to this divided by 2 times of this. The ratio is the same, right? So this divided by this should be equal to this divided, or this divided by that should be equal to this divided by that. The ratio is the same. So that's why you set up this equation. That makes sense, right? Yeah. This is also the concept for the stoichiometry. If you do just a normal stoichiometry problem, you can also using this ratio setup. Okay, yeah, it's also okay. So once you see the ratio here, but what if we have 0.05 moles of the methane, then how much heat they're going to, how much enthalpy or how much change of the enthalpy it will generate it? Well, the same thing, right? So the enthalpy change for this reaction will be just what we have. We have this, right? We have these equations. So generally, your setup equation, 1 mole of the methane gas, that's equal to negative 890.4 kilojoule. This is the link or the conversion factor you're going to have. So what we have is a 0.05 mole of the methane. This is what we have. You just need to convert the moles of methane to the heat. Since you know 1 mole of the methane equal to that much heat, okay? So that's why we talk about this is stoichiometry, okay? It's doing the same thing. You multiply the conversion. The conversion is between moles of methane and heat, okay? You want to cancel the methane, right? You cancel the mole of methane. So you put 1 mole of the methane in the bottom and put how much heat? Negative 89.04 kilojoule on the top. Then you can figure out how much mole of the methane that how much heat that can produce. 0.05 times 890.4. Then we got a negative 44.5, negative 44.52, and this is in kilojoule. Make sense, right? Okay, this is also stoichiometry. Again, if you want to using the ratio to do this also, you can do this. 1 mole of the methane, and the bottom part is 0.05 mole of the methane. That should be equal to 1 mole, then you have a negative 890.4 kilojoule, and then you're looking for this. You still can solve the problem. And what is this solve? Do you know how to solve this? Just go cross, right? You go cross. So negative 890.4 kilojoule times 0.05 mole of the methane, and you're divided by 1 mole of the methane. Then you're doing the same thing. Make sense, right? Okay, so doesn't matter how you do this. This part is generally where the textbook telling you, but you can do the same thing in the bottom parts because stoichiometry, it just talk about ratios. Okay, just talk about the ratios. All right, so let's look at one of the questions in the study guide. Okay, so let's just look at the first two. I think when we're done, and generally we're done for today. Okay, so the first two, well, maybe, yeah, probably we're done. So let's see. Here it says, what is the change of the enthalpy of these reactions for reaction of 4 more of the SO2 with 2 moles of the oxygens? Okay, so if you look at this, 4 more of this SO2, 2 more of the oxygen, generally those are completely reacted, and then they are going to generate the SO3. And we have the equation, and we have these numbers shows over here. Okay, yeah, so the meaning of this is, if we use up 2 moles of SO2 react with 1 mole of O2, then they're going to produce 2 more of the SO3, and meanwhile they're going to produce that much heat. Okay, so if we using 4 moles of SO2, so we should double this. That makes sense, right? But if you're just want to using stoichiometry way to say, first you need to find the connection between heat, between the delta H and the moles of the SO2. Here is 2 moles of the SO2 is going to produce negative 196 kilojoule of the heat. It's not a 2 mole, or it's not 1 mole, it's not a 4 mole, it's 2 mole. This is the important part. You need to find out. You need to find out how many moles of SO2 we need to produce the heat that is given. Okay, yeah, this is the important part. It's not 1 mole, it's not 4 mole, it's not 3 mole, it's 2 mole. This is coming from these equations. Okay, so let's say we're looking for, we have 4 mole of the SO2. So if we have a 4 moles as SO2, and then you just multiply the conversion factor. Since this is conversion factor, you're gonna put the 2 moles of the SO2 in the bottom and put the negative 196 kilojoule on the top. Okay, so then you will see that's gonna be just a 4 times this number divided by 2. Okay, let's put it into the calculator. 4 times 196 divided by 2, and you got a negative 392. Negative 392, and this unit is kilojoule. Okay, so that means 4 moles of SO2 will produce negative 392 kilojoule of the heat. Okay, after these reactions. And again, the negative sign here, that means this is exothermic. So if we talk about, this is the same thing when we talk about release 392 kilojoule. Okay, this one is talk about release 392 kilojoule. Is same, just like a negative 392. Why? Negative means exothermic. That means it's releasing. Okay, producing. Okay, so if we talk about releasing how much heat, then they just talk about, this is a negative sign, shows over here. Any questions? Okay, so the next part is going further, and just to let you know, this answer is not right, so we need to finish this equation. Okay, this one is talk about 2.4 gram of the SO2 instead of 4 moles of SO2. You see? Okay, then what we're gonna do? Stoichiometry. So first thing, you gotta convert the gram to the mole. Okay, and again, every time here, the connection here is talking about moles of something versus heat. It's not talking about gram something versus heat, right? So you have to convert that to the mole first, instead of doing the heat, instead of using gram. So you need to find, okay, the mole of the SO2 should be equal to mass over molar mass, right? We talk about the mass over molar mass, 2.4 gram divided by molar mass of SO2. So as sulfur is 32.066. And you're gonna plus 2 of the oxygen, 15.9994 times 2. Okay, and then you will got a mole of the SO2. And we got 0.03746. And that is the mole. Okay, we're going to use the mole first, and then we convert the mole to the mass, to the heat. Okay, we're using mole to convert mole to the heat. And again, this setup, okay, we can do this exactly the same thing, but again, you still can do the setup like what we talk about. So we have a 2, then this is negative 196 kilojoule. So 2 mole, none. And how about 0.03746 mole? How much heat it is? And you just set up this equation. Okay, so this ratio should be equal to this ratio. Okay, yeah, the same thing. And then you can set up again, you're doing the cross, which is the question mark should be equal to negative 196 kilojoule. And your time 0.03746 mole, and you divide by 2 moles. Okay, very, very important. This number doesn't mean 1 mole of this one, you generate this heat. You need to look at the equation to figure out how many moles of this to generate the heat. Are you clear? This is a very, very important part to solve this kind of question. So now the question mark here, that's going to be just equal to 196 times 0.03746 and divided by 2. And we got a negative 3.67. Negative 3.67. And this one is in kilojoule because the mole and the mole canceled. Now you have a kilojoule. And this is the answer. Okay, this is the answer. It's still exothermic reactions, but they produce much, much less because the amount of the SO2 is much, much less than the 4 moles. Make sense? Right? Okay, so this is what we call the stoichiometry, but this stoichiometry is involving the heat of combustion and reactions. So that's why I'm saying stoichiometry is the most important part in chemistry, okay? And in the titration lab, I mean, we're going to do the lab 50, lab 70. Titration lab is most of the important part is calculation on stoichiometry. This is another version of the stoichiometry. So there's a different kind of the stoichiometry involved in chemistry. But the key over here is still, as long as you figure out the relationship between the one thing and the other thing, and then you can do the calculation just like what we shows over here. Okay. Yes, Carter.
Do that ratio in any way, right?
Yeah, you can also do the ratio if you want, because stoichiometry, major stoichiometry part is still just a ratio. But the stoichiometry, the backbone of the stoichiometry is the mole to mole ratios. It's just moles. But sometimes you need to find a different way to get a mole, right? Over here, you need to, if you're giving you the gram, you need to convert the gram to the moles, right? And later, when we talk about solution stoichiometry, you need to, based on the solution molarity and volume, to figure out mole. So this is the different way to get the mole of the things and then figure out the stoichiometry. Got it? Okay. All right. So definitely for sure, you need the practice on this part. And I will also going to assign some of the homework on the study guide. All right. So let's just open the study guide. I'm going to assign some of the homework. Okay, so page 2. Question number 3. Hey, question number 5. Page 3. Question number 1. And question number 3. Okay, so here, page 3. Don't do this as a multiple choices. Okay, don't do this just as the question 2, 3, 3 and 5 in the page 2. Okay, just write down your work. Don't just give me a multiple choice like a D, C, something. Okay, you're gonna write your work down. Okay, show me your work. And then I probably and let's turn to the page 5. Question number 1. Question number 2. And number 3. Okay, so this one again, question number 1 over here, show your work. Okay, number 2 and number 3, those are concept questions you can write down. Okay, so what is the enthalpy, is endothermic? What is the sign? Okay, so make sure you know the sign. Make sure you're understand the sign related with the endothermic or exothermic. Okay, yeah, so this is pretty much what we're going to do. 1, 2, 3, 4. Those 7 questions. All right, so this is what we're gonna have for the homework. And now we can pack our stuff and go to the lab.